discuss something. This is the load testing of a railway under bridge that we have done using the concepts which we have learned in our UG, mostly in the BTech. So we have this ILDs, right? So we usually learn influence line diagrams, and from influence line diagrams we try to find out the maximum bending moment, and absolute maximum bending moment, absolute shear force. So this is like a real scenario where we used those concepts which we learned in UG. I'm not even talking about what we have learned in PG. So this is like a UG level analysis, and we use this for the real testing of, or a real testing for a railway under bridge. So this project we have done. So railways actually, I think Central Railways. So Central Railways have invited us to do a load testing for the bridge. I'll give you a brief background of that bridge. So this is Dound railway station. Dound is actually about 200 kilometers from Sholapur. So this is in Maharashtra. So you can see
Bro,
it's a junction. Yeah, sorry.
Can you share the PPT?
Oh, okay. Sorry, I think I missed it. Yeah. Sorry, I'll. Yes. So yeah, what I was telling is this is a load testing of a railway, and now you're able to see my screen, right?
yes, bro, yes, bro.
Yes, yeah. So this is a railway under bridge load testing, and we have used influence line diagrams in this. So this is actually a down railway station. This is in Maharashtra. So this is in Maharashtra, and it is about 150 or 160 kilometers from Sholapur. So you can see this part. This is a junction. You can see. So once you know how the junction is built up, right? You have several platforms over here, and then slowly all the platforms, all the railways converge to two lanes. There's two lanes. One is up lane and one is down lane. Okay. So the problem over here is, from the railway station you have one railway crossing. So we can have, so there are two types of railway crossings, right? One, you can either have a overbridge. You can have a railway. What do you call? It's like it's on overbridge. ROB. It's called railway overbridge. Or the second part is a railway underbridge. So this one is a railway underbridge. Okay. So this railway underbridge was a one lane road. It's only a one lane road. Let me write it with some other link. So railway underbridge is a one. It's like a. It's only a one lane road. Okay. So because of this one lane road, what is happening is, whenever you have traffic coming in and going out, there is huge traffic jams over here in this stretch. This entire stretch, there is a huge traffic jam, and this has become a very big political issue over there. And politicians were involved, and they want this railway bridge to be extended to another box over here. So once you have another box coming up here, it can be a two lane. So one lane can be here, another lane. It will for the opposing traffic. So they wanted to have another railway bridge just adjacent to the existing railway underbridge. So this was constructed using. They went and they have designed this. You can see this. This is a two-way bridge. You can see this is a two lane. You have, this is one cell and this is another cell. In there is another one which is also existing, right? There's one more thing which is existing, but right now they wanted to construct a two lane two cell box culvert. It's a two cell box culvert. So this is their cross sectional view, and this is their longitudinal view. So it will start from here. Traffic starts coming from here, and it exits here. Okay. And you can see there is railway tracks. This is a railway track 1, 2, 3, and 4. And they also wanted to have a future railway track if there is another lanes coming in. Okay. So the entire length will be about, I think this is about 40 meters, I guess. This entire longitudinal section from here to here, it is about 40 meters. So this is the background. Okay, so now how they are going to construct? So if you are aware, usually there are two types of constructing these under bridges. One, they can entirely excavate the soil, so they'll just simply excavate entirely this, whatever the soil over here is there, they'll like excavate everything and they'll lay it. But that is actually a big problem, because if you excavate this soil, right, then you need to stop entire your railway traffic in between these sections. So this down railway station will not be operative. So that was long. They have actually this process excavating and then laying out was long back stopped. They stopped it long back, and they have a second procedure which is called box pushing method. So in this case, like in this is the most modern method, and they'll be using this kind of a box pushing. So what they'll do is, let us say this is a ground level. It's a ground level, and you have soil over here. And let me draw it in a new slide. So what they'll do is, this is a soil. Okay, this is a soil strata, and you have ballast and all this stuff here. Sorry. Yeah, you have ballast and all the things over here. Why is it? Okay, so what they'll do is, let us say this is embankments. They'll actually construct. So what they'll do is they'll construct a box culvert somewhere near to their embankment. Okay, this is already constructed. That means it's a precast box culvert. It's already constructed, and then they will actually they will kind of attach a sharp steel kind of sharp steel members over here onto the fronts of the box culvert. So the box culvert will be something like this. Okay, so to these front edges, which are actually progressing edges, you will have steel plates, which are sharpened steel plates were kept here, and then you will have a lot of hydraulic jacks over here. So you will have jack over here, and at the bottom, at the other side also you'll have jack. And using this jack, they'll try to push this entire box in this direction. So they keep on pushing this box. So when they keep on pushing this box, this keeps going underneath, and slowly it keeps going, coming out and coming out. So similarly here also keeps going out, and it comes out from this side. Now that's how they are not even disturbing the um, surcharge on the top side, right? So this is just a gentle, they keep on pushing it. I think they will take about a few days to actually push. I don't know about how many days they have taken, but they'll take few days. So gently they keep on pushing it, and it is not disturbed, so trains can still keep moving on the top. So you have this ballast and you have railways. Train tracks can the tracks are intact, and trains can keep moving. So that's how that's a plan. That's called box pushing technique. So now what they have done is they have casted this box culvert. They have already casted this box culvert in situ, and now right now it is precast. So the problem is because of the COVID. So what happened? This was cast in situ in March 2020, and due to COVID, there are some issues, and the site engineer was not able to figure out his as-built reinforcement inside. So there are two types of drawings. One is a uh, sectional or structural design or structural drawings. So in structural drawings, usually you have reinforcement detailing, right? Reinforcement detailing. So these drawings will be used to understand what will be the reinforcement, what kind of reinforcements are going to come, what diameter, spacing, if there is a development length, how much development length you need to give, and all the things. And once you have constructed it, there is something called as built drawings also. You need to also give an as built drawing. It usually has both architectural and both structural. So it should also include how much you actually placed and what are the architectural dimensions also. Architectural in the sense your cross section details, like if your slab thickness is 150, but after laying your slab, if the thickness is 151 or 152, you will exactly mention those details there. So this guy, the engineer in charge, who was supervising this task of this thing, has lost this as built structural drawings. So now they are not sure about what kind of reinforcement went into these box culverts, and they had issues to push this in under this thing, because they, as you know, the railways are very high. They don't have any margin of error in terms of safety, right? So they are still in doubt whether they want to use this under this, or they can push this, or whether this can sustain those loads, railway loads, or not. So that's where they came to us for doing a load testing on this beam. Oh, sorry, on this culvert. So they gave us these drawings. They also uh, the only inputs which we got is this drawing. That's it. Only input that we got is these drawings, the length, dimensions, everything. These are the drawings that we have obtained. So this we try to break it down. So now we need to understand the adequacy is nothing but whether it is safe or not. So at the end, the single line answer is whether it is safe or not. That is the only thing which the railways need. For that, there are two types of analysis. One, we can do an entire load test. Load test is nothing but, right, like in my first class, if you remember, I was telling you that load test is nothing but it actually gives us the truth, the real truth. So it is the ultimate truth. So load test is truth. The second one is a rebar mapping. So what we can do is that guy has forgot, or that guy, uh, like the documents actually went. Yeah, when he was shuffling his offices, he lost his documents. So he wanted other thing. What we can do is we can either map the rebar. So nowadays we also have this rebar mapping equipments. So what we can do is, like, let us say you have a slab. This is a slab. This is a slab, and you have reinforcement bars, longitudinal reinforcement like this, and you have a transverse. So these are reinforcements which are going in your slab. Now you can bring a scanner, rebar mapping or rebar scanner. It looks like it looks like an X-ray kind of a machine. I think we also have one of such scanner. JB sir, if you remember, we have this scanner. We were also
Yeah,
testing last time.
it is called profometer.
Profometer, yes. So
We have in the lab.
yeah, we have in the lab. So it also gives us at what depth we have the reinforcement, and also what is the reinforcement present. So it will also give the diameter of reinforcement. It gives diameter of the reinforcement, spacing also, and also cover. So how much is the cover? So these details are also okay, right? Once we know these details, then we can say that we'll just compare with the structural drawings, and then we can go ahead and say that yes, okay, this is also safe. But still, railways don't want to take any risk, because what if the profometer readings are slightly off? Then they don't want to take any risk. So that's why they wanted us to go for a load test. So for the load test, what happened is, yeah, load test again, we try to break it down into two parts. First one is we want to analyze the member. So this is a box culvert. This is a box. I'm just drawing a line diagram. We wanted to do an analysis on this box culvert. So what does the box culvert analysis, like, again, what is the main aim of analysis? Analysis should give me the load demands. Okay, whenever you are doing your structural analysis, right? Whenever you're doing structural analysis, then what At the end, what you'll do, you will only find out maximum moments, shear force, or deflection only, right? So the analysis, again, the same thing we have processed, and we want to find out what are the load demands. Okay, then what are the load demands? Thank you. Next, from the load, again, to know the load demands, then what are the inputs we need? One, we need to make a decision of the critical wheel loads. So this is again, here we make use of influence line diagrams. So if you remember, in our line diagram concept, if it is a simply supported beam, so right now our loads are actually train of loads. We have train of loads going from one end to another end, and then we'll see at what location or at what position the load should be placed such a way that this beam is going to experience maximum bending moment. Okay, that we need to find out. This is first step. Next, ILDs and critical positions. So ILDs and critical positions will be found when we know the decision on critical wheel loads. So usually in our textbooks, we will be given a train of load with so and so kilonewtons of load. Each one is having about some kilonewtons of load, and both are spaced between spacing is about 1 meter or 2 meter or something, right? So these are lucky, we are lucky that we will be getting these information beforehand. But here we need to generate this information, because we need to also understand what kind of trains are moving on that uh, on the on those tracks. So we had to read a lot of railway, what do you call, the railway booklets. They have several locomotive engines. They have double headed diesel engine. There is one more called double headed. One is with 22.5 ton loading. Another one is about 20, this is about 25 ton loading. So we try to see several combinations. So each, you can see this, right? Each wheel represents this what do you call, this plus sign, or this circle. This represents one wheel load. So these are three wheels, and then you have a space of 9.5 meters, and then you have another three wheels. And similarly it keeps repeating with each wagon, or each what do you call, each bogie. So we try to see several combinations of these train of loads. So this is a train of load. So if you can see, we have several combinations, and we try to place over it. So now what happens is that, see, this is how the train goes on this. Now you have, I'll just play the animation. I'll try to see whether you're, see, this is one train, one kind of a train. So I need to have such combinations to see which combination is more critical. Okay, because I need to test that combination which gives me maximum bending moment when compared to all other combinations. So this is how the train actually passes. So this is my box culvert, and train is going from this direction to this direction, and these are my loads. So if I just try to draw, I'll try to draw one. I'll try to draw a line loads. So this is my. Uh, so I this can be simply shown in this way. Okay. So each wheel is going to take. So each, actually there are two wheels. If you see, there are two wheels always. So each wheel load is going to take about 25 tons. About 25 tons. Or 22.5. There are some more locomotive engines where it is going to take about 37.5 tons also. But we were said that the maximum allowed traffic in this is about 25.5 tons. So we have taken one combination which is giving us very high load demand. And in this, if you see, so what are the other loads we need to take? So one load is, we have considered the live loads which are coming from the locomotive engines. You can see these are the live loads coming from the engines, which are directly engine which is giving us the loads. The second one is, you have self weight and track ballast also. Okay, you have self weight of the top slab, and you have track and ballast load. So I know I hope you know what is ballast, right? Ballast are the coarser aggregates which are used in trains. You can see this, right? But once you have a ballast and then you have sleepers over which you have your track. And over this you have your wheels going on. Okay, these are ballast. So we have this self-weight track and ballast. So these loads are actually always there. Okay, you'll always have this loads onto your structure. I think I someone has any query?
Bro, soil also exerts some pressure on the walls.
Yes, yeah, that is called lateral earth pressure. So if you see here, we have considered the lateral earth pressure as well.
Okay, okay, okay.
So you can see this, right? So this is my lateral earth pressure.
Okay,
Okay.
okay.
So if you see, the lateral earth pressure is always a trapezoidal kind of. If you have a surcharge onto the top, so just again geotech, some geotech refreshing. So refresh topic. So you can see if you have a surcharge onto the top and you have a retaining wall. So this load up to this part, you will have something like this. This is how your load will be acting, right? This is your retaining wall, and this is your ground level or soil level. So this is how your load keeps acting. So you can see. So we have considered that as well. Again, you have this soil coefficient of friction, K values, and all those things. Those everything were considered. You can see this is how the soil at pressure acts. But surprisingly for us, we have considered both the cases where there is no soil earth pressure and there is earth pressure. So when there will be no soil earth pressure at the ends, right? When your track is going to come out of this embankment, there you will not see any lateral earth pressure. And we have also checked for that combination also when there is no lateral earth pressure. So here this combination does not have any lateral earth. So this combination does not have any lateral earth pressure. Okay. So okay, here I have already mentioned without any lateral earth pressure. So these are the loading combinations. So we have checked this, and this is because of the reaction getting from these loads. So even this will act some kind of a uniform loading on the bottom slab. So now what we'll do is with these loads, we tried to run ILDs, and what we found is that this combination with these combinations, the loads when the loads are, if you remember, my previous slide showed me how much these are the actual train of loads. So with these train of loads, you can see always some part of the wheels are always outside the culvert. Okay, because these are actually, I think these are about 9 meters plus almost 3.6, I think 14 meters apart, I guess, last two wheels. So some wheels are always outside the culvert, I mean the box culvert. So what we have found is we have run the analysis to see, even this is done again in StatPro. So what we did is we tried to run the analysis, and we found out that this is going to be our critical section. So when my loads are at these points, then I'm going to get a critical. And again, when I say critical, it should be both. It should be, first thing is bending moment maximum. Second one is shear force maximum. So bending moment, again, you have two types of bending moments: hogging and sagging. Hogging and sagging. Okay. So yeah. So next part, we have again used another combination. This is again another combination, and we tried to get another combination of our ILDs. So this is my another combination, and even here you see. So you can see, right, the loads are actually not, they're kind of varying. When the in this case the LD should be at this point, and in this case the LD should be at this point. So from the analysis, what we observed is the top slab AB. You can see in the top slab AB, the maximum bending moment at the joints. So you can see the maximum bending moment at these joints are about this much, and in the maximum bending moment at the mid span, So at the mid spans, so at the joints are nothing but these are hogging bending moments, and the mid span usually we have a sagging kind of bending moment. And the shear forces were this much. And the remarks we can see these are because of combination one, and this is because of combination two. This is because of combination one, and this is because of combination five. So this is how we try to obtain the maximum bending moments. And instead, I think you have this feature where you can run a train of loads. So train of loads can be run along your loading sections. So this is directly from the stat. So instead, what I have given is I just let me just show what I have done in the stat. So stat analysis was very direct. So I have simply created one box culvert. Yeah. So what I try to do in the stat is I just created one culvert. These are having the dimensions. Yeah, this is a straight line. So you have these dimensions, center to center distances. Whatever we have obtained, and these I have modeled it as springs. So bottom I have modeled it as springs because this is a soil surface, right? So we'll have, you can't model simply like a, so I have given some springs. So how, this when you model it as a spring, you need to give spring stiffness also, right? So for spring stiffness I have used subgrade reaction, subgrade what is it called, subgrade stiffness, sorry, it's called subgrade stiffness or subgrade reaction also. Maybe you might have learned these things in geotech. So subgrade reaction I have considered. For each type of soil you will get these subgrade reactions. It is, I think, denoted it as Ka. So it will be again similar to your Newton per mm or Newton per meter. So I have considered for this soil, whatever the soil which we have in the site, I have used that stiffness, and I have given it as a uh, I have given that stiffness to this. And then these are all the same. The way you guys do your analysis, similar kind of. This is a trapezoidal loading. Okay, these are trapezoidal loadings, and these are similar. And there is one option in StatPro. Usually in StatPro, you can give train of loads. Let us say first you define your train of load. What is your distance, and what are the loading? What are the loads of each points? And then you can also give how many steps it has to move, uh, how many steps it has to move, and for each step it keeps on finding out the maximum bending moments and maximum shear forces. Okay, this can be done in StatPro also. Okay. So from those analysis we have obtained these maximum bending moments, and even in this case we have obtained these maximum bending moments. And then we have zeroed down our loading criteria. How do we load the structure? So at what point do we need to load, and how do we load the structure? So this is the final loading profile of the structure. So we need to load this as a 43.5 ton. This is 43.5 ton. This is 43.5 ton. From the edge of this box culvert, this 43.5 ton should be at 630 mm, and from there on, this is 1.85, 1.85 meters, 1.5. Because, like I mentioned, these are the wheels, right? Train. And if you see, these are our strain gauges, and these are the locations of our strain gauges we have placed on the top. And these are again locations of our strain gauges we have placed on the bottom side. And this is for the maximum, you can see it here, maximum hogging bending moment. So if I place my loads in this way, I'm going to get a maximum. You have a hogging bending moment. This will be maximum. And if I'm going to place my loads in this fashion, this is going to be maximum. This is my bending moment diagram. So this is going to be maximum. So this we try to figure out, and we finally zeroed down our loading, how we need to load this structure. Okay, so uh, now the problem now, we try to understand what should be the loading, how do we need to load, and what should be our loading configuration. Everything was now zeroed down. Now the problem is, see, these see at the end, what we are trying to do is we are trying to replicate the real scenario where the wheel loads are going to act on this structure. And you need to understand that right now we are taking about 43.5 tons. This is my design loads. Okay, I have taken 1.5 times of our actual loads. Okay, so first thing is, how do we load this? And these should be a point load. This cannot be any UDL, or it cannot be an area. Anyone having an? I hear some. Raghu, you have any doubt?
No, bro.
Okay. Yeah. So we want this to be a point load, because we want to replicate the real life scenario where the train is actually moving on the top of it. So first thing is, see, if you see here, the figure was so small, but see, this is actually the place where they have casted it, and the front portion you can see right there. You can see the soil here. They'll be pushing this box into the plane, and it goes inside the soil there. So now, if you see here, we can't bring the train on the locomotive and place it on top of this beam, right? In that's not possible, first thing. So how do we replicate the actual loading onto this beam? So that will be our second part. Now what happened is, maximum bending moment in the beam due to the train of point loads is this one. And we can do two things. One, we can do an equivalent UDL that generate equal maximum bending moment. But one problem is, if you say that, if you convert this into the equivalent UDL. So usually this is how the analysis is done. Usually, even in the designs, right? They don't consider these high point loads. They'll only consider it as an equivalent UDL. But we don't want to consider that as a equivalent point load. The only reason is, if you convert this into an equivalent UDL, you can get you can match your bending moments, maximum bending moments, but you can't match your deflections. Okay, you can just simply make one small point. What you can do is, if you have a simply supported beam, let us say a simply supported beam has load P acting at mid span. So what is your maximum bending moment? Maximum bending moment will be PL by 4. This is M. And what is your delta at the midspan? PL to the power 4 by 48 EI,
PL
or PL
cube.
cube. Yeah. So if you have similar UDL, let us say you have same equivalent UDL. How do you what do you how do you say that it is equivalent UDL? This UDL should give you the same bending moment PL by 4. So let me just, what is the maximum bending moment in this case? WL square by 4 should be equal to PL by 4. WL square by 8 should be equal to PL by 4. So this goes off, and W is going to be 2P by L. Okay, so this should be 2P by L. In this case, what is our delta? Delta is going to be WL power 4 5 WL power 4 by 384 EI. So if I substitute this, 5 W is going to be 2P by 384, all right, into PI. This is L cube, and this is going to be 10 by 384. Okay, 10 by 384 PL cube by EI. This is due to UDL, and this is due to point load. Can you compare these two values?
Yes, bro. Actually, UDL is giving higher deflections.
Yeah, UDL is giving higher deflections, right? So then you can't simply do an equivalent UDL study, because you are simply UDL will give you a very much a higher what do you call higher deformations, and then that is not going to be an equivalent, and that will be more conservative as well. So what we wanted to do is we wanted to replicate and simulate the similar kind of a loading scenario that we get uh, uh, on the real tracks. So for that, how do we distribute the loading? So first we need to distribute those loading. We what we try to do is, you can see these tracks. I I'll just stop for some time. I'll just ask. I'll just ask if you have any doubts. Any doubts so far? Like, you understood the. Anybody? Any doubts? You're able to follow what I'm trying to say.
Bro, I have a doubt, bro.
Yeah.
Bro, you said that the single wheel load is 25 kilonewtons,
Yeah.
but we have two wheels now, bro. We have to take 50.
Yeah. So see, that's what the concept is. Axial. It's called axial load. Single wheel means it's a single axle. So single axle will take about 25 tons.
Okay, single axle contains two wheels, bro.
Yeah, axle contains two wheels, right?
Yeah,
So
okay,
one
okay.
one on the left track, one on the one
Yeah,
track, another one on the another track, right? So yeah, so yeah, it is an axle load. It's not. See, it's an axle load, but when we do analysis, right, we'll take it as a single. We'll take it as it is acting on one point, which is at the midpoint, and that will be 25 tons.
okay, okay, okay.
Others, I'll also take this opportunity. I'll just ask others whether they have installed, because now I see other students also have joined. So did how many of you have installed the software, Abacus? Oh, yeah, you are able to. Are you able to? Yesterday you said that you have some issues, right, Abhishek? Now you're.
Yeah, I removed the 2020 version and installed 2019 version. Every time I try to open it, I have to patch it again so it can run.
Okay, fine. What about others?
Sir, on a similar note, just now when you said the axial load has 25 kilonewton, does each railway line one single take 25 kilonewton load, or it gets divided into 12.5 on each side?
See, that's what 12. It's actually 12.5, 12.5 on each side.
Okay, okay.
Okay,
My question
so
was, since you told the whatever they gave was 25 kilonewton as max, so I wanted to know whether 25
20,
kilonewton per this rail was that.
Ye- yes, yes, it's an axle. So see there, even when you're designing your traffic bridges and all, right? So you'll always consider a axle road. See, what does an axle mean is, like, you have one axle, and then to this axle you'll have two wheels, right? So
Yeah.
usually they say it's a axle load. It's not wheel load. So each axle can take about 25 tons. Okay, that means you have a reactions of 12.5 here and 12.5 here.
Okay,
Okay.
okay. I understood now. I was thinking maybe 25 on each side.
No, that will be too high. So then it is like a 50 ton.
Yeah, that's what
See,
I wanted to ask, whether it is 50 or 25.
no, it's 25. It is 25. Just to add to that, we have this freight corridors also, right? Freight corridors are which carries the freight. Freight is nothing but the what do you
Goods.
call
Load.
goods, yeah, loads, goods, and all stuff. So in these freight corridors, usually it was designed for 37 and a half tons. So it's like 37 and a half times 1.5 will be the design loads. But these are not the freight corridors. That's why we were asked to go only up to a maximum of 25-ton wheel loads.
Okay, okay, I understand.
Others? What about others? Did you install the software? Okay, fine. We'll go ahead with the presentation. So once we have obtained the load combinations, or like where the load has to pass, or where see, okay, one announcement. Please try to, okay, Srinath, you're able to get, okay, you have installed the software. Others, okay, one. So almost I think about 4 or 5 students have already installed. Okay, fine. See, students, actually, we waited for about 10 minutes. So, uh, like, what we assumed is that you have not installed, and that's why I started with these experiments. But today, what I'll do is I'll finish this off, and from tomorrow onwards, we can again resume our tutorials in Abacus. I hope that is fine. But you please try to join at 7 a.m. 7 p.m. so that we'll have again a clear idea. Otherwise, see, I started talking about this experiment analysis, and then yeah, okay. Others also, just if you have not installed, you can ask your friends. See, others have already installed, right? You can ask them about the procedure of how to install it, so that we can, from tomorrow onwards, we can start. Okay, okay, I'll continue now. Thank you. So this is my like this is my instant. Let us say my train is going from left to right, and when my train is right at this point, I'm just taking a screenshot or a photograph of my train. When it is right at this when my wheels of that train is right at this position, then I'm going to experience my maximum bending moment here. Okay, so for that, what I need to do, I need to just place my loads in such a way that they are actually at these points, and these loads has, each point has to carry this much of load, 43.5 tons and 43.5 tons. So for that, one way is simply we can design. So if you see this here, what we try to do is, this is you can see this part, right? This top layer, this top part is nothing but our railway. This is our railway track. This is an I section. Okay, and on the top of the railway track, what we have done is, if you see, this is beam A. You can see this part, right? This is beam A. Okay, this is one beam. We have welded one beam on top of the railway track. So you can see one, two, three beams. So three beams were placed, and now whatever I load on these beams, if I keep loading onto these beams, what happens is that these beams are going to distribute the force onto the railway tracks as a point loads, right? You understand what I said? So I'll just try to draw it in the next page. See, what happens is that, if this is my railway track, it is an I section. On bottom, I have my sleepers here. So you have several sleepers. Usually sleepers are trapezoidal sections, but just for simplicity, I'm drawing it as a square. So these are my sleepers. Okay, underneath sleepers, again within sleepers, you have several ballast. So you have ballast layer, and underneath that you have your soil. So this is your ballast, and this is your soil, and these are your sleepers, and this is, so what we have done is, we tried to design we designed a beam which is an I section, and we tried to place it on the railway track like this. Okay, and then Now let us say if I, and then we placed one beam on top, on again on top of this, and then another beam on top of this. Then we kept loading here. This entire part was loaded. Now tell me, if I'm loading this entire part above these beams, now on to the track, this is my track, right? This is my track. So you are seeing track in the longitudinal section, okay? This is the longitudinal section. If you see from this side, the track looks like this. It is also an I section, right? So when you're loading this entire beam onto the top of it, the reaction has to come from this. So these reactions are nothing but my wheel loads. The wheel loads. Okay. So I need to load these beams in such a way that reactions on these beams has to be same, and that those has to be 42.5, whatever we have mentioned over here, 43.5.
Bro,
Understood? So yeah,
bro, the dissection beam length is equal to gauge length, bro.
gauge length. Which gauge you're talking?
Railway, the track gauge, this bro.
No, no,
This.
no. See, railway gauge is, see, when the gauge is nothing but center to center distance of each railway track. This is a one railway track. You have sleepers underneath. I'm seeing that this is my top view of the railway track. Okay,
Yes.
and this is our gauge length. I think this is about 1.67. I think if for it, sorry, for 1.67 meters. For a broad gauge, for a meter gauge, it will be 1 meter. And sorry, this is a medium gauge, I guess, 1.67. Yeah, but what you're saying is not a. You're saying the length of what?
Length of I section beam, bro, on which the loading is acting. That one only, bro. I section beam. You are placing I
Okay.
section beam on the rail.
Yeah, yeah. Okay, I'll show you. Okay, now I'll show you a 3D. Then you'll understand. So this is how we have placed it.
Okay.
So see, this you're saying that this length is going to be the gauge length, right? Whatever the gauge.
Yes, bro. The
So
green one.
this cannot be gauge. Yeah, I understand. So this cannot be a gauge length because we need some overhang portion also. Because
Okay.
if we have some overhang portion, only then we can actually distribute the load equally here. Now what we need to do is when we place the load above these, so you can see this is my railway track, okay,
Hmm.
and above the railway track I have beam A, okay, and above the beam A I have beam B. There is another beams which we have designed, and these are beam B. So you can see these beam B's are like with some different, we have given some spacings over here. Okay, so now when we keep on placing some weight onto the top, now we need to get a reaction force of, both should give a reaction force of how much? 42.5. And also this part and this part should have a 21.25 and 21.25 each. So that's why we have designed, we have to design it as a overhang beam. You understand?
Yes, bro.
Yeah. If it is directly equal to your what do you call your
Gauge length.
yeah, directly gauge length, then we may not directly get this as 21.5. Maybe because some part will be shared by some part of the beam and other part will be shared by other part. So you will have a proportionate loading there. That we don't want to have.
Okay.
Okay. So yeah, this is our configuration. So this is how we. So now how do we load it actually? Because see, now we said that we have these beams designed, and then these beams are designed for this much of load, because beam should not fail. Na? At the end, if beams are failing, then we are entire thing is going to fail. So we have designed these beams. Onto top of that, we need to have loads placed. So usually the procedure is people use a lot of sandbags. If you remember, like even when you're doing a load testing, pile load test and everything, usually they start filling the dead weights by sandbags and all. But luckily, this is a railway project, so they have several sleepers, normal the sleepers which they use it, right? So they have several of them lying around. So we have used these sleepers, and these sleepers cannot be as per our wish or as per their wish. This has to be stacked slightly logically, because if these sleepers are stacked in some random way, then the loads are going to transfer. If these are transferred in some random way, what happens is that the loads are going to transfer more in this side and less in this side, which we don't want. So for that, what we have done is we have also figured out the sequence of stacking the sleepers. How should we stack the sleepers, and what should be the how many numbers of sleepers has to be stacked in each layer. So we with that we have given layer wise stacking sequence. Let me show you that. So in this, if you see, if you want these loads to be acted, that is 42 or total weight of that 135.5 tons, we have also measured the weight of each sleeper. Each sleeper is about 300 kg. So then we need about 438 sleepers, and those 438 sleepers we try to stack it in this sequence so that my reaction forces will be equal, and also I'll be getting the required wheel axial loads onto my track. Okay, this maybe now this I have showed already. So you see this is my beam which is placed on the railway track, and then these are the secondary beams. On these beams we have stacked the sleepers, one above the other, one above the other, in different layers. So one thing is we need to also control how the stacking is done. We should also supervise whether they are stacking it correctly or not. So here you can see this is the real photograph of the bridge testing. So this part we try to do some DIC also. This maybe I think JP sir will tell about some DIC aspects, I guess, in future. So we tried to do some DIC on the natural light. So we did not use any extra source of light. We have used natural light to do some DIC analysis. Uh, just um, just one clue is like DIC is nothing but digital image correlation. Okay, I think you will also learn about this in your further classes. Visual image correlation. So you see here, right? So this is how we envisaged, like, this is how we thought about our loading, and you can see how we have stacked. You can see the same similar way we tried to stack one above the other, one above the other, and one above the other. And these are the things which I'm talking about. I'm telling you, right? This is my beam A. You can see this beam A, beam A. So on the beam A, you can see this is my beam B, and above that we kept on stacking. So once we have stacked it, you can see how it. I think we went up to 14 layers of stacking. Only then we will achieve the uh, actual what do you call actual load level which we wanted. So let me keep it in a full screen. Sorry, yeah. So you can see it here. Then here also we stacked it. See, now we are just simply stacking, right? Then how do we know whether it is going to take the given loads, or it is going to be safe? How do we justify that whether it is safe or unsafe? So for that we have placed some sensors. Okay, so what happens is that you can see these wires over here, right? These cables. So under this cable we have a LVDT, which is called linearly variable displacement transducer. It is called LVDT. What it does is it tries to measure. It will measure displacements and deformations, whatever it is. So it tries to measure the displacements. So we kept on loading this. We kept on loading this, and we tried to see how much is the displacement at this section. Yeah, can you see this part? This is that LVDT. So we placed it here, and whenever you have load coming in, this part actually gets pressed. So it looks something like this. So you have a probe here. So whenever some load is acting onto this, the probe gets pressed, and how much if what like the extent of this compression gives us how much is the displacement. So we have also measured this displacement here. Okay, and you can see this is my axial load, and this is my maximum vertical displacements. and you if when we kept on loading it, so these triangular markers shows that these are my actual data points. You see, when we kept on loading it slightly, the displacement also increased, and it only increased up to 1 mm. 1 mm is hardly L by, I think the it is about 4000 span, so it's L by 4000 or something, which is like, very much under the serviceability limit. And also we have measured the strains also. So I hope you know the strain. The strain is nothing but deformations by uh, displacement or deformations per unit length. So we have also measured the strains using strain gauges. So we try to check. So we started. You can see it here. We actually started loading at about 9 a.m. in the morning. Finished one loading at 5 a.m. in the evening. So this was a very long kind of a loading schedule. So even in that cases, you see the cracking strains. The cracking strains of concrete is usually 0.00014. This will be the cracking strains, initial cracking strains. Even after the initial cracking strains, the reinforcement comes into the picture, and then they'll also start to contribute the resistance. But if you see in all the way during the loading scenario, the strains never touch the cracking strains. The strains are much lesser than the cracking strains. So then, and also visibly, we try to see whether there are any cracks, or if there is any if there is any cracks, or if there any spalling and all. But at the same time, we have also used this data from strain gauges and the LVDTs, the displacements, to check whether we have any to check whether any um, to check whether if there is any cracks, or if there is any if the load has kind of cracked the cross section, or if there is any spalling. So once we have done this, there fortunately we never saw any cracks, or we never saw any abnormal displacements. Like you can see it's almost 1 mm only, there's it did not go even beyond 1.5 mm. And also if we fit the curve, these points we try to fit a straight line curve, and it is almost straight. We say this is almost linear. When it is linear, then what we'll say is the structure is in elastic. Sorry. So what happens is that when you have load versus displacement plot which is linear, then what we can conclude is structure is in elastic regime. So when the structure is an elastic regime, that means once you load it, it displaces about some time, it goes for a displacement of some amount, and when you unload it, it will come back, and it will retrieve its path. So once we unload it, then it goes back, but we didn't wait for it to unload, because loading itself took about 9 8 10 hours. If again unloading will take another 10 hours, so we didn't wait for it. But what we thought is, when we fit a curve, it is almost linear. Then we said that the structure is an elastic regime. When the structure is an elastic regime, there is no uh, issue with there's no issue with safety. So it is always safe when the structure is in elastic zone. So that we have with that we have concluded that the structure is not going to fail, and they can go ahead with the placement. They can do a box pushing, and they can place inside their embankment. So if you see, these are the two comparative images which I have placed. One is this is the time when we have when we went for testing. So once we have tested it, then we asked them to when then we gave a report saying that it is safe inside the under the bridge. So now right now on the top of it, you have this railway tracks passing, and even you can see the traffic also. There's a plane traffic over here. So now there is no traffic jam as well on this structure now. So whenever you travel to Pune, actually this is on the Pune route, Pune Mumbai route. So you'll get to see this down station. There you can see this RUB. So even the traffic is going well there now. So that is about the experiments that we have, I mean, the real testing that we have done on the site. So if you have any questions, you can ask me. Any questions?
Bro, I have one doubt.
Yeah.
Bro, you said that you stacked about 438 number of sleepers on the beam.
Yeah.
How can we get that number of sleepers, bro?
Yes. So number of sleepers in the sense, like you were asking me whether
Yes,
how
bro.
do we like how to get see here you can see there's this calculation here, right? So see the total weight which we need is 130.5 metric tons. This is from our analysis only. If you add these 43.5 plus 43.5 plus 43.5, it will be 130.5 metric tons. Okay.
Okay.
And each sleeper weighs about 300 kg. This
Okay,
actually we
bro.
have also ensured it, and then that's how we got these sleepers. And that's, see, we can put 438 sleepers in any order, but we wanted to do it in a sequential order so that we'll have a right division of the forces, and each support should give me the same kind of a support reaction. Okay, that was ensured.
Okay.
Okay. Any other doubts? Others? Sir, JP sir, you have something to say?
Uh, yeah, Prithvi, actually, the plate load test when we are doing, so we have
Yes.
kept the load, which is equivalent to the axial load on the box girder. But here,
Yes.
coming to the earth pressure, so anyway, earth is there, it undergoes some pressure. But
Yes.
have you considered the surcharge effect on that?
Yes.
Because
Yes.
in the
Yes.
design, generally we consider the surcharge, but when it comes to
Yes.
the when you are doing the plate load, have you taken any surcharge additionally?
Yeah, that's actually a very good observation. So what we have done is, so if you remember when like during the this 43.5 was actually without any including the surcharge. So when we say this 43.5, this uh, this configuration where the wheel when the wheel loads are placed in this configuration, this was actually with the surcharge load only. Okay, so we have also placed some surcharge onto the top of the beam, because that's how we have actually asked them to create entire surcharge. Whatever in future we are going to see the surcharge, like you have some part of embankment with soil compressed, I mean the compacted soil. On top of it you'll have ballast, and top of it you have the track. So that was actually replicated in the testing as well. So they have almost laid a track on a small length of about 14 meters of track onto the on during we when we are testing it. You can see it here, right? You can see a lot. There is some embankment, as well as you have ballast, and we have sleepers, and on top of it we ask them to have this railway track. So that was placed, sir. That was placed. Yeah, here also you can see we have placed some earth and then ballast, and then
Oh, here the culvert when you are testing, it was not in use, right?
Yes, it was not in use. We have only one lateral, and only one side we have lateral earth.
The
So
other side it is not
yeah,
there.
the other side it was not there. So even that was taken into the calculation.
Okay.
These maximum displacements, right? We have considered that there is only one. I mean, the lateral earth was there in one side, and the lateral earth was not there in the other side. That was considered.
So it was like a model box girder.
Yes, yes.
Any questions, students? Generally, the people who are doing design of these box culvert are also, they won't get exposure to witness the plate load test experiment.
Yes, 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 yes.
Very few people will get the experience.
Yes. That was actually a very good experience, and also uh, this is again, see, usually what they use, what even railways, what they asked us to do is to do a simple what do you call, sandbags kind of a test. You do a UDL and then you test it. That's what they said. But we wanted to go for this kind of a point load test only, because like I mentioned, this is going to, that those are going to give a very conservative kind of a design estimates. So what if there's no rebar, and because of that conservative loads, what if it is going to fail? Then it will be a disaster there, right?
Yeah,
So
yeah.
we
We have to replicate the actual scenario. So
scenario, yes, correct.
that is always better.
Yes,
And
yes,
in olden days, since the cranes and all were not there, they used to use
yes.
these sandbags and all.
Sandbags and all, yes, yes.
Mm. Now the
Luckily
cranes
we
are
were
there. So,
yeah, the cranes are there, and even the machinery manpower was too many. If you see,
yeah.
I think about, we got about 40 manpower there when we are testing, and there are about three hydra cranes out there with us.
Mm.
So the machinery was, we have done it, we have about three load combinations there. We have done it in 2 days. One load
One more question after this, sir.
Yeah.
But you have checked the what is that? I mean, the displacements using LVDTs and DIC on the box cutter, right? Have you
Yes, yes.
kept any sensors for the these I section girders
I section girders, actually we have designed I section girders for three times its load
capacity?
capacity.
Okay,
Yeah,
capacity.
so that's
Okay.
why we did not keep it. And even if, see, we could have used some strain gauges also, but
Mm-hmm.
see, inside again, it's, the difficulties.
Yeah, yeah,
The cable length has to be like in 40 or 50 meters long, and if you use strain
We
gauge, if
won't get power also.
we won't get power. Actually, we were using DG power there, and the problem with strain gauges are, if we have 40 meters of length, cable length, right? So strain
Mm.
gauges will not be useful, like, because of the resistance. The cable length increases its
Okay.
resistance, and your sensitivity will be very bad. So that was one of the reason, we wanted to cut down a lot of sensors. So we used, that's the main reason we used DAC. But one interesting fact is, when I used this DAC, right, I have
Mhm.
kept my tripod onto the other side, and because
Okay.
of, whenever the train moves, right, my tripod is shaking. So the DAC readings were gone. Like, we never used those
Okay.
DAC readings.
We won't get accurate levels.
We won't get any accurate result. So whenever the train moves, this is going to vibrate. The tripod is going to vibrate. So yeah, this is the cutting edge which I was talking. If you, in the starting I was saying, right, this is the cutting edge. So from the backside they keep on pushing it, so it keeps on cutting the soil through it, and then it moves forward. So everywhere now wherever you see RUB constructions, they'll use this technology.
Even in Hyderabad, near Secunderabad also, seen three box girders.
Yes, yeah, 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 correct. Near that rail bhavan, right? Just in front of that rail bhavan, railway bhavan. Yes. Any other doubts, others? Train load is 1.1, but you're taking 43 point the extra 6 kilometers due to surcharge. 40 taking, right? Mhm. Yeah, okay. I forgot to mention one thing. So there is something called dynamic effect as well. Okay.
In fact,
Yeah, yeah, impact. It's called dynamic impact factor (DIF). So yeah, including that, it was about 42.5. I'll just mention what does the dynamic impact factor means. So usually when 25 point when I say 25 tons, so 25 tons is like a static load, right? It's a static load, but when the train moves, it's a dynamic. It's like a dynamic forces moving, right? So because of that, usually we'll have a dynamic influence factor or a dynamic impact factor (DIF). So this DIF will have several factors based on different combinations. So this DIF was shared by RDSO on the railway drawings board, the railways board. They shared us what this DIF was, and because of that, we are getting about this 43.5 amplification factor. So we can't simply design for 25 tons. We need to have an amplified we need to have an amplified loads for it to actually do a real simulation or to actually design for a real railway moving load. So yes, you're right, Raghu.
Yeah.
It is not exactly 1.5, but we have used some dynamic influence factor.
Got it.
Yeah, any other dots? Others? JB sir, what do you think? Like, shall we? Uh, I think others don't have any doubts, I guess. But right now it is 8:20. So some students they said that they have installed this software. So
mm,
you shall we shall we quick like you know shall I recap
yeah,
these?
sure, no
Uh,
problem. Yeah,
I'll
no
just
problem.
do a I'll just do a quick recap. So uh, I'll
So
just
maybe
see
in
how
20,
many.
25 minutes you can cover that.
Yes, I'll cover that. I'll just show maybe. So what I request is Abhishek, Srinath, Shiva Kumar.
And
Please open your softwares and you just go through. You have some. Uh, you just try to open the software and see what all things you have in that. I'll again simply go through all the modules which we have done, what modules we'll use for what purpose and all, so that now itself you'll get comfortable with the software. Is it okay? Please tell me if it is fine or not. Srinath, Shivakumar, Abhishek. Okay. What about others? Yeah. Okay, so I hope now you are parallelly doing I think you are parallelly uh, working on the software also. So now let me open the software Abacus. So Abhishek, Shiva, which what versions do you have? 2019. Abhishek said 2019. What about Shiva Kumar? Shiva Kumar, what version do you have? Okay, fine. Okay, that's okay. So now again, if you so this is again the part module. My next topic which I'm planning to which I'm planning to start is a coupon test. Okay. So today what I'll do is I will not model it, but I'll say what are the steps that we should do, that will be doing it in while we are modeling it. I'll just give uh, a brief background on these coupons, why these coupons are used, how these coupons are used, and what are the what are the test uh, like what tests we'll do using these coupons, and what are the outputs we are going to get from this coupon test. And then we'll say, and then we'll discuss about why do we need to model these coupons, and then we'll see how it is also modeled. Okay. So when I say coupon test, right? So if you see, um, so far we are saying that steel is having a Young's modulus of about 2 into 200 GPa. Poisson's ratio is about zero point 0.3. Yield stress, if it is a mild stress, about 250 MPa, and then ultimate stress was about, like, say, 400 or 450 MPa. How do we say these values? Like, why, like, how, who is saying these values, and how, if he's saying these values, and how is he getting those values? So for that, they'll do a tensile test. Okay. Okay. For that, to know those values, they'll do a tensile test. So now there should be a generic way of doing a tensile test. Okay. What does a generic way mean? So if I'm cutting some sample, okay, if I'm cutting a sample from some plate or rebar or whatever, and I'm following some procedure in my lab, the same person, or, like, similar kind of a research group who is testing the same thing in some other lab, uh, he's getting some value. These two values has to be comparable. Okay. When this can be comparable, when we have a same environment. Okay. So environment means what? Environment means the dimensions should be the same. Dimension should be the same. The rate of loading should be the same, and also you have temperatures and other should be the same. So if this should be the same, then there should be some body which is governing these values. Okay. Those bodies are nothing but the statutory bodies. In our case, we have IS codes. Okay, which governs these values. Okay. And we have US has ASTM codes, ASTM standards they call it as, and British codes, we have British standards. So similar kind of these codes. So we need to follow these codes to have a unified kind of a thing, because it should be generic. Because if you, for example, you keep testing a lot of compressive strength of these tubes and cylinders, right? So why only 150 by 200 300? You can say that it is because of size effect. You say that this because of Saint Laurent's principle, your length should be two times, at least two times of your diameter, so that you will not have any stress concentrations. But you can also have 200 and 400, right? 200 diameter and also 400 diameter cylinder. Or why only 150 by 150 cube? See, that's a generic way of doing it, and it's a generalized way, because once, if you are testing your concrete, I'm hearing a lot of disturbance actually. Yeah. Okay. So there should be a generic and also a generalized unified way of testing this. Okay. Similarly, we have those codes for these coupons also. Now, what are those coupons? Coupons are nothing but, let us say you have a uh, yeah, coupons are nothing but, let us say if you have a See, you have a plate, okay, or you have a rolled I. Let us say it is a ISMB or whatever it is. Like let us say it is ISMB 300. Okay. Now, if you want to check the material properties. What is the material properties which I'm saying? What is the Young's modulus of the steel? What is Fi of the steel? And what is your ultimate stress of the steel? What is your fracture strain? And you can also check elongation or percentage elongation. How do you check from this? You can't simply bring the entire ISMB beam and then you can't apply tensile load directly, okay, because that is not the right procedure, right? So what you'll do is, instead of doing that, let us say you have an I beam like this. What you'll do is, instead of that, you'll cut a small strip from this beam. So let us say you have cut one small strip from that beam, which is looking like this, and then you can test this under tension. So you will clamp it here and you can clamp it over here, okay. But there is a problem with this kind of a arrangement. What happens is, when you're testing a beam, a strip, so what you'll do is you will exert a tensile force and you will see what is the stress and what is the strain in between this section. But in this case, what happens is that, because if you remember you stress concentrations, so what does the Saint Venant's principle? We have the Saint Venant's principle. What does it says is, wherever you have the forces acting, there you have a higher concentration. So at these places you have a higher stress concentration. So these places you have a higher stress concentration. So if you have higher stress concentration, your what do you call, your strip is going to fail at this position only directly. It is failing. If it is failing here, then it is actually not giving you the real stresses. It is giving you a stress concentration. So this stress concentration is nothing but, usually, let us say if you have 400 MPa acting at mid span, here your stresses will be about 500 MPa, and this is exactly not replicating your actual scenario. So you can't use directly, you can't use this kind of a strip. So for that, what the code says is, you use a dog bone shape. So it is a dog bone shape. Okay, it's similar to the dog bone. So in this way, if the shape is like this, what happens is, when you are pulling one end and when you're fixing another end, you'll fix this end and you'll pull it. So here the cross section is higher, right? So if the cross section is higher, then the stresses are lesser, and then you will not have any breakage happening, and then slowly you will transition to lower cross section, and here you will have a uniform stress. So this will be a uniform stress zone, and this part we call it as gauge length, okay. So the code has given the dimensions, what should be the dimensions of these coupons, okay. So we have to cut. So if anytime, like in future, when you wanted to know the material properties, usually the material properties will be provided by the manufacturer. If you're buying it from Tata Steel will give you the data sheet of that steel properties. But when you're doing research, right, so it's better from the data sheet, and in addition to your data sheet which the manufacturer is providing, you always cut such coupons, and then you test it under tension. And then you find out what is your Young's modulus, yield stress, ultimate stress. So how do you find your Young's modulus? So the Young's modulus can be found. What is Young's modulus? So Young's modulus is nothing but your slope of your stress strain curve in elastic zone. So if you have, this is your stress strain curve. So I'm drawing it. I'm drawing for a very high strength, not high strength steel, maybe a HYSD or a slightly higher strength steel. So this is your stress, and this is your strain. So usually in these cases, when we have a very non-linear kind of a stress strain behavior, what we try to do is we'll try to bring up a concept called a proof stress or a proof strain. So proof stress is nothing but, yeah, this is proof stress. So proof stress is nothing but you will take 0.2% strain, and then you will draw a line parallel to your initial slope. Let us say this is your initial slope, and you'll draw it wherever your that line which you're drawing is going to touch your stress strain curve. There you call it as a yield strain. That is nothing but, this is yield strain. So frankly speaking, you shouldn't call it as a yield strain. You should call it as a proof stress. Okay. And initial slope, I was talking about this initial slope, right? What is this initial slope called? This is nothing but Young's modulus, E or Young's modulus, or the elastic modulus. Okay. And this is your yield stress. And after it starts, after it starts yielding, you have this regime called, I shouldn't use the top space, I guess. Whenever I'm using this space, then it's going back. Fine, I'm not going to draw there. So this regime is called strain hardening. So strain hardening usually happens up to your this ultimate strain. This is ultimate strain. So this is strain hardening. And after that, see, from this point, this is your maximum ultimate stress as well as your ultimate strain over here. This strain is going to correspond to your ultimate. This is your ultimate strain, correspond to your ultimate stress. Okay. And after that, slowly, once the stress starts to drop, then it's called softening. This is softening. And during the softening, the necking, you can see, this necking, right? So initially the section is like this, but after that ultimate, then it starts to neck. So the area of cross section starts to reduce very fast after this ultimate point. And this is called softening. And after certain point of softening, then you'll have a sudden break. It breaks down. It has to come down like this. Yeah. This part is called fracture strain. So this is your fracture strain. Okay, this is about the complete history of this stress versus strain. How, what we'll get and how do we get, why do we measure, how do we measure this yield stress, strain hardening, strain softening, and all. So for this, like I mentioned, we'll be doing a coupon test. So for that coupon test, what our next exercise is, we have done some coupon testing. So you can see these coupons. You can see yeah, you can see this coupon. So this part is a coupon, this is a coupon, this is a real coupon, and this is the drawing of the coupon. So this drawing is as per ASTM standard. So to be precise, it is ASTM E8. The number is ASTM E8 standard. So this we have tested, and you can see this small part over here, right? It is called a strain gauge. So strain gauge, the function of strain gauge is it gives the strains. And you can see this clip, right? It's called a extensometer. It will give you the extension, and this is nothing but a strain gauge. Strain gauge gives the strain, extensometer gives the extension. Extension divided by the initial gauge length is nothing but strain again. So indirectly it is also giving you the strain values. So this is a machine, this is a Flexure FTM 250 kilonewton capacity machine. So what we'll do is we'll keep this coupon inside these grips. So you can see these are these are the grips. Okay, we'll keep this coupon inside the grips, tighten this. So these are tightened, and then this will be pulled up. So when it is pulling up, you can see this is going to resist that load, and whatever the load is resisted, it's called load resisted, and load resisted by area gives you stress. So again, the basic definition, mostly I think you know about this as well. What is the basic difference between stress and pressure? Stress is nothing but load resisted by area of cross section. Pressure is nothing but load applied by area. Okay, so stress is always the resistance. Whenever you have a resistance, then you will be then the material is being stressed. So load resisted by area is your stress. So now whenever you are applying the load using this grip, the material tries to resist that load, and that divided by the area of cross section. So area of cross section in this case is how much? This part only. This part is width, and you have thickness in this direction. That will be your stress and strain. Okay, so these are the dimensions. Maybe you can just take a screenshot of this, or maybe otherwise I'll just post this this thing in the group today. What I want you to do is, I'll post this. Okay, once the class is over, I'll post this problem. So what I want you all to do for today, after installing the software, is you try to generate, or you try to model this shape, coupon shape. Okay, and try to come tomorrow with the shape of this coupon. Only the part, you can model the part of this coupon, and tomorrow we'll try to tomorrow, yes, from tomorrow onwards we can start analyzing, but you try to come with this part modeled already. Okay, you can I'll again share this coupon and details of the coupon again. So tomorrow what we'll do is we'll model this coupon, and this time we'll try to use shell elements. Okay, shell elements. So the first day is like day before yesterday, we have used one-dimensional beam elements. So otherwise these are also called line elements. Okay, second day, which was yesterday, we used three-dimensional elements, 3D elements, and tomorrow we'll use shell elements. Okay, so you try to replicate, you try to draw when you're using the part. Okay, I'll give you some hints also what you need to do. So in this part, okay, when you have this module, which is part module, go to this create part. In this modeling space, you opt for 2D planar, deformable, and base feature should be shell. Okay, this is the only clue which I wanted to give, and rest of the thing you try to figure out and try to draw. So here again, rest of the thing is simple AutoCAD kind of a drawing. You try to explore these things. So here you have a fillet. Here you can make a fillet also. Okay, what is a fillet? Fillet is nothing but this curve. You have a transition zone, right? This radius R, this is R, this is R, and this is R. So this is a transition zone that you need to model using this fillet, and the rest of the things are same as what you do in AutoCAD. So once you model it, then we'll try to see. Here we actually have an experimental data also, right? This is actual experiment. We'll also see. So now the inputs are not nothing. I did not give any inputs. Inputs, the dimensions, at least, yeah, dimensions I have given here. But what are the other things you need? Material properties. So material properties I have given it over here. And what are the other inputs? Boundary conditions. So boundary conditions I did not exclusively mention, giving you a picture of how the coupon was placed. So with this picture, we'll get some idea of what should be the boundary conditions, and we'll apply those boundary conditions, and we'll analyze it, and we'll see how we are, like, what results we are going to get. Is it fine? Is it okay? You're able to follow? Yeah. So what's your task for today? Like, what should be? Yeah. Okay. Thank you. What's your task for the next class? So you need to. I'll share that presentation slide. So you try to model that. Okay. Thank you. You need to model that coupon and keep it ready for the next class. We'll analyze it, and we'll try to find out the results from those coupons. Okay. So yeah, if you have any doubts, you can ask from the first part of our lecture, or even the second part of the today's lecture. If you have any doubts, you can raise your hand, or you can simply ask directly. You can also you can message in the group if you want as well. Yeah, I think that no one is having any doubt. So far about 4 students have Abacus installed. So I kindly request others also, please install the software. You can take help from the fellow students who have already installed. So please try. Please be prepared and come for tomorrow's lecture, so that we'll have real hands-on training. Okay. Yeah, JP sir, I think the others don't have any doubts, I guess. So shall we call for the date today now?
Yeah, okay, sir. Thank you very much, Prithvi sir. I request all
Sure.
the students, please install in your system and you try to practice. And the videos will be uploaded and I share by tomorrow morning.
Yeah. Okay, sir. Then that
Right.
looks fine.
Thank you, sir.
Okay. Okay. Thank you. Yeah, bye. Good night.
Good night.